All right. Okay, now, first, since all three of you have something in common where you're all planning to graduate in the spring, Dr. Schroeder sent out a reminder earlier today about doing your application for graduation. So, and I don't believe I've handled that for any of you yet. So I don't recall anyway. Sorry if I have. Anyway, get that done. It's one of the deadlines, November 1st in this case, that the graduate school likes to rigidly enforce, including the application itself, which is quick and easy. I mean, you just have SOAR generate it, get it signed one way or another, send it to me, and then I take care of it from there. But also the fee payment from the graduate school website has a link to that, and sending the receipt to like a screenshot of a receipt to the degree auditor, Michael Howell. So get on that sooner rather than later so we don't have any problems. There's been some times where it's been like almost forgotten, like So yeah, it's kind of pain having to take care of graduation related things during the semester before you graduate, because at that point it's not really foremost on your mind just yet.
Yeah.
So, okay. Now, how's homework going? Dare I ask?
There was some couple of weeks ago. I did some corrections and still didn't get anywhere with the one I didn't turn in, but I need to just look at it completely.
Okay. And I've all had other things going on, like my midterm in 560. Okay. So, yeah, I haven't yet decided what else there will be homework wise. Well, because also there were still like 5 weeks or so. You got to figure out exactly what to cover during that time. I had worked through how the method of variation of parameters gets derived for inhomogeneous ODEs, and then the other method for solving inhomogeneous ODEs is method of undetermined coefficients. And I thought, oh well, logically that's next. But then I had this feeling like, I just don't want to. And it's not really all that interesting, because really what you do is you take the formulas for variation of parameters and you say, okay, what if your right-hand side is of a function of a certain form? So you just fill that in there, like, this e to the at for some constant a or whatever. And then you work out the integral as much as you can and see what you have. Like, what type of function is it? Or is it like a linear combination of functions? And that's how the method of undetermined coefficients comes about. It's tedious as hell. You work things out like in a case-by-case basis, for different types of functions, and where you can work out the integral, and it's all kind of boring. So I thought, well, if I don't want to do that, then what should I do instead? And thankfully I thought of something. Okay, that still has to do with inhomogeneous ODEs, but I find there's something that actually came up for my research, and it works out a whole lot more elegantly than undetermined coefficients does. Okay, so alrighty. And these are what are called Phi-functions that are useful for describing solution of a first order ODE. Okay, so the starting point will be something that we've seen before. just the general solution formula. And I'm going to go back to just scalar ODEs rather than systems. But everything I show here can be applied to systems of ODEs, just placing scalars by matrices. We'll have y prime is equal to, say, lambda y plus some function b of t. I don't recall if that's the notation I've been using before, and I'll say past 20 carry. Dang it, that's so annoying. Okay, so y of t is e to the lambda t, y of 0, plus integral 0 to t of e to the lambda. Actually, I'm going to factor e to the lambda t out. 0 to t, e to the minus lambda s, e of s, ds. Okay. So now what I'm going to do is, because the thing is, with the problem is the function b of t can be anything. So, so because it's arbitrary, I can't do anything with this integral. I just have to leave it written as an integral. And it would be nice if there was some way to not have to do that, to get a solution formula that doesn't require integrals. And actually, that is possible by using a Taylor series for b of s. So Taylor expand. B of s. And also, just for laziness, I'm going to let y of 0 be equal to 0 because this term over here has nothing to do with what I'm covering today. We don't need it at all, so I'm just going to get rid of it. So now I have e to the lambda t integral e to the minus s, or minus lambda s. You better put in the sum, j equals 0 to infinity, of jth derivative of b at 0 over j factorial times s to the j ds. Okay. So now what I'll do is I'm going to pull anything out of the integral that I can. So e to the minus t. So I can certainly pull out the summation. Anything that doesn't depend on s, I can pull out. So I'll have that fraction, jth derivative would be at 0 over j factorial. And now I have the integral as little as possible. E to the minus lambda s, s to the j ds. Okay. Okay. Now, so now all that's left is, like I said, I want a formula that doesn't require integrals. So now I just need to evaluate b's, and I can have that. What would I need to do? How would I go about evaluating any of those integrals for any value of j?
By parts?
Yeah, integration by parts. Now, so what I could do is, if I were to, so I'm going to define, okay, so let's, I'm I need to define phi j. I gotta be careful here about my notation. Actually, before I go any further, since I have e to the minus lambda s, so I get that lambda in there, which is a constant, and then I have just plain old s to the j. But I'd like to have things a little more unified. So I'm going to multiply and divide by lambda to the j, which seems kind of strange, but then what I can do with that, actually, I need to use, let's see, do I need minus? Okay.
Phi j over phi j.
Yeah. Right. Or lambda to j or lambda.
Sorry, lambda j over lambda j.
Yeah, but I'm not sure if I want to do that. Because when I integrate, like for the simplest case, if j equals 0, I'm going to end up dividing by lambda just for the integral. Okay. Like, because the subject is Phi-functions, so I've not yet introduced, but I will be able to once I work on this integral. So I'm just going to be careful with my notation so I don't get myself into trouble later. Okay. Okay. All right. Let's just see how this goes. Okay. So I need to do some work on the integral first. So now I have e to the lambda t sum over j of all this stuff. Okay, and then I have 1 over lambda to the j out front. And then inside the integral, I'm going to have e to the minus lambda s. And then I have lambda s all raised to a j power. That's why I did this. So I could have just lambda s throughout. So every s is paired with a lambda. And now what I want to do is make a u substitution. So I can let u equal lambda s. So then du is lambda ds. In other words, ds is 1 over lambda du. Okay. So now what I have is equal lambda t, infinity, j0, j factorial, 1 over, oh, it should be lambda 2j power. I messed up here. I had lambda sub j, it should be lambda to the j. Okay.
I forgot my glasses.
Oh. All right. So now I have another factor of lambda intruding here. So this would be 1 over lambda to the j plus 1. Integral from 0 to, well, the limits are going to change now. So if s is equal to t, then u is equal to lambda t. Okay, and then I have e to the minus u to the j du. All right. Alrighty, to make sure that I haven't made any mistakes at this point. Okay. Now, let's look at the simplest case of j equals 0. So that's this integrals from 0 to lambda t at just e to the minus u du. So now I have minus e to the minus u with these limits plugged in. So now I have minus e to the minus lambda t minus a minus, which makes a plus, then 1. Okay. So now what I can do is, if I then take this e to the lambda t and multiply through by this, then here's what I get. My first term of my solution is going to be b of 0 over 0 factorial, which is 1. And then I have e to the lambda t minus 1 all over lambda plus a sum, j equals 1 to infinity, of all the other stuff. So in other words, this is the first term of the solution corresponding to the j equals 0 case. If I just work out this term for j equals 0, I get b of 0 from here, and then this is the other thing I get. And so a very important point, I had this from the integral, but then I took this and multiplied through by it. So, and then that's incorporated in here. Okay. So any questions about what happened here, or at least for a j equals 0 case?
Okay, but I'm just trying to understand. So the j equals 0 case, it just correlates to everything but the sum, and then the sum of everything else covers all the other terms.
Yes.
Okay, okay.
Yeah, we'll only get j equals 0. So at least for that case, I didn't actually have to do integration by parts, because the integral was simple enough that I could just work it out. All right, so let's make this note here. Okay. Okay. Oh, just gonna take a picture of this now that the board is full. Okay. Now, for any other j equals 1, 2, 3, and onward, I will have to do integration by parts. But what I'd like to do is try to see if I can simplify that process a little bit by doing a recurrence relation, like see how higher powers of j depend on a result for lower powers of j, since I already have a result for j equals 0. Okay. So I need to find psi of t. So not phi, but psi. You can't get the phi function just yet, but as an intermediate step, to find psi of t, be e to the lambda t. Oh, I need a subscript. E to lambda t, integral from 0 to lambda t of e to the minus u to the j du. So the actual integral that I have from before. So now I know what psi 0 is. So that's e to the lambda t minus 1 over lambda. Okay. So if I do integration by parts, what I hope that will let me do is write each other higher order psi function in terms of a lower order one. So integral of e to the minus u to the j du, using integration by parts formula, it's going to be, so e to the minus e to the minus u to the j. Okay. Plus integral j u to the j minus 1 du. So that's just what the integration by parts formula would give. Now here I've written it as a indefinite integral, but now I want to throw in the limits. So 0 lambda t okay. And then if I multiply both sides by e to the lambda t, like I have up here. This table in the way is really annoying. All right. So now what I have on the left side is exactly psi j. So psi j of t. And this integral over here times e to the lambda t is psi j minus 1. So now I need to plug in the limits. So I'm going to have, okay. And we're assuming that j is greater than or equal to 1 in this case. So for instance, when I plug in the lower limit of 0 in here, I'm going to get 0. Okay, so I'm going to have minus, okay, so the e to the lambda t from out front, and then I'm going to have minus e to the minus lambda t times lambda t raised to the j power, okay, and then plus j psi j minus 1 of lambda of t. Okay. So now what I have is a recurrence relation. Each psi function depends on the previous one and has this term added on. Okay. But now I can simplify this because this e to the lambda t and this e to the minus lambda t will cancel. So that's going to be minus lambda t all to the j power plus j psi j minus 1. Okay. So now I don't have to do all these tedious integrals. I can just define each psi function from a previous one. So what I can do now, since I have the first one, I have psi 0, this one right here. I can use this to see what more of these functions look like and see if there's a pattern to them. Are there any questions about what happened here? How am I doing on time? Oh, not a whole lot left. Okay. So, all right, so now I'll do some examples. Let's see what happens when we get to j equals 1, 2, and so on. I can take a picture of the board the first time, I hope. I'm pretty sure I did. Yes, I did. Okay. Okay. So for j equals 1. So according to this, we have psi 1 of t would be equal to minus lambda t plus j, which is 1, plus psi 0 of t. And then we know what that is, so I'll fill that in. Okay. All right. So what I'm going to do now is I need to put all this over a common denominator. All right. Something doesn't look right here. That's kind of bugging me. All right. I mean, I know what the result is supposed to be. Okay. So if I multiply this by lambda over itself. Okay, so then I'm going to have e to the lambda t minus 1 minus lambda squared t over lambda. And that is totally wrong. That is absolutely not how it's supposed to turn out to be. All right, what did I do wrong? Dang it. Okay. Well, okay, because as far as the integration of parts is concerned, if I go back to, this is really good for not being fully prepared. And I have worked out stuff like this before, just not, okay. So I have, yeah, e to the minus u to the j. So it worked out beautifully the first time. The mistake is likely from integration by parts. Okay. So all right. Of course, integration by parts, I was presented using u and v, but I have u's all over the place. But this is playing a role with my u function, and this is my dv. So that would be the correct v. That would be the u. Local limits. Minus a minus makes a plus, and then I take the derivative of this, which is ju to the j minus 1. Yeah, so then when I plug in the limits, I have minus e to the minus lambda t to the jth power, minus the value of this at 0, but j is at least 1. So when I plug in 0 for u, I'm going to get 0. And these exponentials cancel out. Okay. So what on earth went wrong? What I'm supposed to get is I'm supposed to get a lambda squared in the denominator, and I've even minus lambda t minus 1 minus just plain lambda t. So in other words, this square is totally supposed to be down here. So, and that's what is puzzling. Okay. On the other hand, oh, I see the problem. Okay. I defined this incorrectly. Because based on this result here, the only reason I get this is not equal to this. This is equal to the numerator. And then I had an extra 1 over lambda floating out there, and I put it in here. Okay. So I need to include that in the definition.
Oh, okay.
Because for this to work out at j equals 0 to become this, I need that 1 over lambda sitting there. Because this, yeah, so this part without the 1 over lambda gets to be the numerator.
Okay.
And divided by lambda. Okay, that will fix the problem. Okay, so now I include that here. Okay, and then I have all this, and all of this is multiplied by okay, right. That's helping. And then that gets multiplied through all of this. 1 over lambda passes through and becomes part of this. So yes, so now what it really is lambda minus quantity lambda t to the j over lambda. And that ought to work. So now I have this. Minus lambda t over lambda. And that simplifies to become just minus t. Okay. Then what I do is, okay. So again, common denominator, I multiply and divide by lambda. And I have that. Okay. Although, what still bugs me is I was supposed to have lambda squared for a final result. So I might need to rethink the definition again. Okay. Right, so then if I have lambda to the j plus 1, okay. Oh, right, so okay. Tweaking as we go. And I'm almost out of time. All right. So to make it work out the way it ought to, I need to have lambda to the j plus 1, which actually is what I have in the, if you go back earlier, actually, if I can peek at the notes here. Yeah, lambda to j plus 1. So yeah,
so we just dropped it.
Perfect. That's what I need. Okay, so then this still applies for j equals 0 case. So then I have lambda j plus 1, and then I have lambda j plus 1, and then this is lambda to j plus 1. But then what happens is over here, like when I include over here, this is for psi j minus 1. I only need 1 over lambda to the j for that one. I still have an extra factor of 1 over lambda. So I include that in here. J over lambda. Okay. So okay. So I'm just going to rewrite this because it's so messy. Okay. So first I'll rewrite the recurrence, so it's neater. The recurrence actually works. So this is, rewrite this neater also. Psi j of t equals 1 over lambda j plus 1 e to the lambda t times this interval. Okay. So that's the definition that works. Okay. The recurrence relation, okay, is psi j of t is equal to minus lambda t all raised to the j over lambda to the j plus 1 plus j over lambda psi j minus 1 of t. Okay, so these two things work after much trial and especially error. All right, but that's what you do. You find what works and keep tinkering with it if it doesn't seem right until it does work. Now, let's do some examples. J equals 1. Psi 1 of t is equal to minus lambda t over lambda squared plus 1 over lambda times psi 0, which is already known to be this. Okay, so now we have a common denominator of lambda squared, which is what's supposed to be. So now we get e to the lambda t, e to the lambda t minus lambda t, or minus 1 minus lambda t, all over lambda freaking squared. Okay. And I'll quickly do one more. I know I'm out of time. J equal 2. So lambda 2 of t is minus lambda t all squared over lambda cubed minus or plus j equals 2 over lambda. Okay, and that'll be e to lambda t minus 1 minus lambda t all over lambda squared. So you have a common denominator of lambda cubed, but yeah, my definition is still not quite what I want it to be, but it's a lot closer than it was. 12 by a scalar multiple. So now if I'm going to have 2, I'll just leave that out front. And I have e to lambda t minus 1 minus lambda t minus, and because I have a 2 over here, but I don't have 1 here, but I'm having a common factor of 2 throughout, I have a 1/2 lambda t squared all over lambda cubed. Okay, I don't like that 2 being there, but I'll put up with it. Okay, so I probably have to do something, deal with like a factorial or something. Yeah, because if I keep going to do j equals 3, I'm gonna have a factor of 3, so this will become a factorial. Okay.
Okay. So it'll be, you say become a factorial, so it's gonna be 6 out front then?
Yeah, but what I really should do is modify the definition yet again, but I don't have time for that now.
Okay.
Okay. So I have my work cut out for me on Thursday. Now, the pattern. All of them have e to the lambda t first, then things subtracted off. You keep dividing by higher and higher powers of lambda. But look at the terms subtracted. Here's just a 1, then 1 and lambda t, then 1 lambda t, then 1/2 lambda t squared. What do these terms come from? Where do you recognize those? Taylor, yes, Taylor expansion of what?
Of e.
Yes, of the exponential. So you take e to lambda t, subtract off its first j plus 1 terms, or terms up to order j of the Taylor series, and then the next, so then it's like all the remaining terms, but divided by lambda cubed.
Okay.
So without having to go for recurrence, if you had to write down ones for j equals 3, 4, etc., you can use that pattern to do it.
Right. So would it be? I mean, when the next one would it be 6 times e lambda t minus the Taylor expansion over lambda to the 6th?
4th.
4.
This,
okay, so that part stays.
Yeah, this power increases by 1 every
each
time. Here we get new factors.
Okay.
Yeah, so actually, I'm going to leave these psi functions defined over here. I'm not going to change the definition again. What I really want are phi functions. So phi j of t is equal to, I'll define it to be 1 over, okay, so that'll be in terms of psi j minus 1 of t divided by, so for instance, I have, okay, so that's phi 1, that's phi 2, that's phi 3, so, okay. So if I define my phi functions like that, for j equals 1, 2, etc., and then phi 0 of t, notice the index is 1 less. Phi 0 of t is just the exponential. I can use these functions, and that's what I will do on Thursday, to write down the solution of the ODE. Okay, what a mess. All right, I will clean this up on Thursday, and also continue from there. All right, well, dang, wow, I've really run over. Okay, see y'all in 26 minutes. And get your graduation applications in.
Yes, sir. I'll do my best.